Hey guys, so this is the reference angle and exact value booklet. So basically what this booklet is looking at is understanding what's happening when we discuss reference angles in a quadrant, and also discussing what happens with the table when we need the exact values for something like sine at 150 degrees or cosine at 2 pi over 3. So this is kind of putting everything together and finding whatever that answer is given some sort of angle. So on the top here, I have theta in degrees for your table. We're going to refer to some of the reference angle stuff here on the bottom. It's a little out of place from where you are in the booklet, but basically if you guys can refer to the front page, I'm going to be going over the booklet, or the table, sorry, at the bottom of the first page, and then you can fill in the reference angle stuff and all that as we go through. Okay, so we're starting at the top here with the theta in degrees. We also want to know theta in radians, and that'll be one of the big goals of this booklet, is not only understanding the exact value stuff, but also knowing how to solve for it in radians. So 0 degrees in radians is 0 radians. 30 degrees is pi over 6. 45 is pi over 4. 60 is pi over 3. And 90 is pi over 2. Remember that these are all angles. It's just a different way of reading angles. 30 gets to be pi over 6 because we multiply 30 by pi over 180, which we did in the previous booklet, and then we do the pi over 180 for all the rest of the angles there. Now we need to find out what sine is equal to at 30, sine is equal to at 45, etc. So when you guys look at the graph here on the bottom, I have it kind of drawn out, and this will help you a little bit with your reference angle stuff as well. And this is going to come into play a little bit more on page 2. But if you have some scrap work you can use on the side, please do. So if I'm at 0, there's 0. Okay, but as I make my way up, let's say that this is my 30 degree or pi over 6 angle. Those both mean the exact same thing. If I look at my x and y value, you may notice that x is fairly larger than y. Then as I make my way up the graph, this one gets me at 45 degrees or pi over 4. This one gets me to 60 degrees or pi over 3. And then we finish off at 90 degrees or pi over 2. As we make our way around the circle, and this is all related to the unit circle, you'll notice that y continually gets bigger, whereas x continually gets smaller. Okay? So that's going to help us with sine and cosine, because if we remember, sine is related to y, cosine is related to x. You have some values from grade 11 that you need to know, like 1/2 and root 3 over 2 and those things, so I'm going to fill those out now. But understanding that sine goes from small to large, and that's because the y value starts at 0 and ends at +1, which is something we should know from the unit circle stuff already, whereas cosine starts at 1 and ends at 0. So sine goes from low to high, cosine goes from high to low, so they're going to be the opposite of each other. So the first value is 1/2. The next value is root 2 over 2, and the final value is root 3 over 2. Cos and sine share these three values, so cosine is the exact same, but in this case it goes the opposite way. Okay, because again, y gets higher, cosine gets lower. All right, as we make our way around the circle, and this is something you're going to see on page 2 in just a moment, we are going to make our way around into the second, third, and fourth quadrant. And when we do that, it's still going to have our reference angles be exactly the same. And this is something that you deal with at the top of the page. So something like 150 degrees is the same thing as, 120 degrees. If I'm at 120 degrees here, that's the same thing as 60 degrees, because it's 180 minus 120. And then if I did 135, that's 45 degrees. And then if I'm at 150, I'm at 30 degrees. Same thing holds for our radian reference angles as well, but we'll see that a little bit later on. Okay, so tan is y over x. So if tan is y over x, that means that, or sine over cos as we saw in the last booklet, that means that we're going sine divided by cosine. So 0 divided by 1 is 0. 1 over 2 divided by root 3 over 2 actually cancels the 2's out. So we end up with 1 over root 3, or it's root 3 over 3 in that spot. And the reason is because you can multiply by root 3 over root 3 for that part of the table. Root 2 over 2 divided by root 2 over 2 gives me 1. Root 3 over 2 over 1 over 2, 2's cancel. I get root 3 over 1, which is root 3. And then 1 divided by 0 we cannot do, so it is undefined or a 0 with a line through it, depending on how you want to look at it. So this is the table at the bottom of the first page, and something that is really important for you to understand. So I mentioned that we would have a discussion of what's going on in each quadrant. So just very briefly, I want you guys to focus on, especially at the start here, just kind of like quadrant 1 and 2. I'm going to zoom in a little bit. So in quadrant 1, we start at 1, 0, which you should know, up to 0, 1, and that's from previous booklets. But then we make our way around to 30 degrees, 45 degrees, and 60 degrees. In those points, we have an x and y value, and if you remember from the last booklet, sine is y, cos is x. So from our table, if I'm at 30 degrees, cosine is at root 3 over 2, and sine is at 1/2. What happens as the angles get bigger? Our y values get bigger as well. So 1/2, root 2 over 2, root 3 over 2, all the way to 1. Whereas our x values get smaller, root 3 over 2, root 2 over 2, 1/2, and 0. And that's because x is getting smaller as the angles get bigger. And you notice that the radian measurements are there as well, something that we'll need to get better at as we go through. Quadrant 2, you should notice that we match exactly the same, and that's because our reference angles here go from 150 and 180 gives us a 30-degree reference angle. 135, 180 is 45. 120 and 180 is 60. And then with the radian measurements, and this is going to come a little bit later, you may notice that 2 pi over 3 and pi over 3 have the exact same point. That's because whatever the denominator is, the reference angle would be that denominator. So 2 pi over 3, reference angle is pi over 3. 3 pi over 4, reference angle is pi over 4. 5 pi over 6, reference angle is pi over 6. The only thing that changes in these points are the signs, and that's because in quadrant 2, x is negative, or from the cast rule, cosine is negative, sine is positive. And that's kind of how you read this entire page, even though you don't have to memorize the whole thing. The note at the bottom is what we talked about on the front page. The higher the reference angle, the higher sine theta is. The higher the reference angle, the lower cosine is, as they deal with y and x. This is your main page that you need to know. This is the table that you will need to write out as soon as you get a quiz or a test. And then this is the cast rule, the 30, 360, 0, 2 pi, or sorry, 0, 360, 0, 2 pi, making its way all the way around the circle. And then you have all your coordinate points along the edges. This you already knew, and this is the new stuff from this booklet. So I'm actually going to skip over example 2 for now. That'll be in part 2 of the video. Part 2 will just basically solve all of our questions. For now, I'm just going to do the notes in part 1. So this is on page 5. And also kind of, it refers to the end of page 4, I guess, as well. Okay, because what we're going to do is we're going to be looking at radian reference angles. Okay, so we did all the reference angles for the degrees on the front page. I didn't go through it in the video, but hopefully it's a review for you from last year. And basically reference angles all refer to the closest x-axis. So wherever our angle lands, the reference angle is wherever that angle is, and then the difference between that and the closest x-axis is always where we find the reference angle. The reference angle is super important because whatever the reference angle is equal to, it's going to allow us to then go back to this page I mentioned and figure out where it is on the table. So if I figure out the reference angle is pi over 4 for cosine, then I know my exact value is root 2 over 2. So that is really important in terms of knowing the reference angle. But what's also important for radians is knowing where we are, because these quadrants, if we remember, are all going to refer to the cast rule. Okay? That, I would argue, is probably the hardest part about radians because we're not used to determining an angle in radians. So this will be our biggest jump. So as we go through, we're going to talk about how we get the reference angles and then knowing kind of where they are on the graph. So if I am at 0 for a reference angle, I'm at 0 in quadrant 1 because it's the closest x-axis. In quadrant 2, I'm at pi. So this is going to be a really good resource for us understanding these 4 axes, which is something you've done already. So I know that I'm at pi because pi minus 0 doesn't do anything. Pi is there. And then I'm at 2 pi once I get to quadrant 4. The nice thing about quadrant 1 is quadrant 1, just like degrees, is going to put us in the exact same spot as the reference angle all the way through. So pi over 6, pi over 4, pi over 3 are the exact same angles in quadrant 1. So there's pi over 6, pi over 4, and pi over 3. Once they get into quadrant 2, now you're looking at a little bit different, right? Depending on, let me just redraw that one there. Depending on where your closest x-axis is. So in this quadrant, the closest one is pi. So on the end of page 4, it kind of has a general equation for each quadrant, but visually, hopefully you guys can see that in quadrant 2, we're going to go pi minus the reference angle, and that's going to tell us where we are in quadrant 2. Well, if I go pi minus, so pi minus pi over 6, I'm going to need a common denominator because that is pi over 1. So every single time we do it in 2 to 4, we're going to need a common denominator. So in this case, it's going to be 6 pi over 6. And our final answer in quadrant 2 is 5 pi over 6. Same thing applies for all these ones. So it's going to be 4 pi over 4 minus pi over 6, which is 3 pi over 6. This would be 3 pi over 3 minus pi over, sorry, that should have been pi over 4. Hopefully you caught my mistake there. 3 pi over 4, there we go. This should be 3 pi over 3 minus pi over 3, so that's going to be 2 pi over 3. And then 2 pi over 2 minus pi over 2 gets us a pi over 2. The other concept for pi over 2 is that you're on the y-axis. And just like 0 being on the x-axis, we should know that between quadrant 1 and 2, for pi over 2, we're always on this line here. Okay, so let's continue on with kind of the harder ones like the pi over 6, 4, and 3. Okay, so if I did 6 pi over 6 minus pi over 6, if I go into quadrant 3, I'm going from the x-axis down into quadrant 3, which means I'm going to be adding pi plus whatever my angle is. Well, if this was 6 pi minus pi, then it's going to be 6 pi plus pi this time. So I'm going to be at 7 pi over 6. 4 pi plus pi gets me a 5 pi over 4. 3 pi plus pi gets me at 4 pi over 3. And then in this case, I could go 2 pi plus pi, which is 3 pi over 2, which is correct. Or I could just understand that I'm at the bottom of the y-axis now. And finally, in this case, it's 2 pi minus. So instead of pi, it's going to be 2 pi over 1. So 2 pi over 1 in this case is the exact same thing as 12 pi over 6 minus pi over 6. Just a common denominator, 2 pi over 1 times 6 times 6. So that gets me to 11 pi over 6. In this case, 2 pi would be 8 pi over 4 minus pi over 4. So that's going to get me 7 pi over 4. This would be 6 pi over 3 minus pi over 3, which is 5 pi over 3. And then this is still going to be 3 pi over 2 because that's still the y-axis in that quadrant. A couple of tricks to know. You may notice that in quadrant 1, all of our numerators are equal to 1 except for the 0 part. And then in these ones, our numerators are always 1 less than our denominator. That will always be the case for quadrant 2. And then in quadrant 3, 1 more than our denominator. Unfortunately, quadrant 4 doesn't have the same kind of trick or pattern, but as long as you know what double your denominator is, because we're always going 2 pi minus, double 6 is 12, so 1 less is 11. Double 4 is 8, so 1 less is 7. Double 3 is 6, 1 less is 5. So this is always 1 less than double your denominator. However you want to look at it is fine. There's also another method that I kind of write out in the notes, where if I count out the numerators, whatever reduces does not exist. If you notice, none of these fractions reduce. So if I went with 1 on top here, I would skip 2 over 6, 3 over 6, 4 over 6. They're all gone. They don't exist. So the next quadrant would be 5 because that does not reduce. 6 over 6 reduces. 7 over 6 would be the next one. 8 over 6, 9 over 6, 10 over 6 all reduce. So 11 over 6 would be the next one. So it's up to you on how you want to remember the counting method or however pattern you see it throughout the table for radians.